Another exercise, like the first one, for part of thermodynamics, when we want to find the internal energy, the work, the heat, the change of state. Sayings of the exercise 2. A container closed by a movable piston containing 2 grams of helium. We consider that the helium is a perfect monoatomic gas. At conditions of pressure P1, V1, adiabatic process is carried out in a reversible process. So the process is adiabatic now, and it's especially a compression, bringing the gas to conditions P2, V2. It means from P1, V1, we pass to P2, V2. Given, knowing that pressure 1 bar, volume 1 is 10 liters, and pressure 2 is 3 bar, you have to determine A, the final volume V2, B, the work exchanged by the gas with the external environment, C, the variation in internal energy, we mean the change in the internal energy of the gas, and finally we have to deduce the variation in temperature, the change in temperature of the gas, without calculating its initial temperature. The data here, gamma, which is well known as Cp over Cv, in this case it's equal to 5/3, R, which is equal to constant 8.32 joule per degree Kelvin per mole. Let's start. So, 2 grams of helium. You have to know 2 grams of helium. The gas is helium, and this gas is considered as a perfect gas. It's a monoatomic gas. Here you consider a perfect gas. A perfect gas. All right. It undergoes what? It undergoes an adiabatic process, compression. So, adiabatic, it's very important to know about adiabatic process. Adiabatic process in a compression way. So, adiabatic compression process. Adiabatic compression process. All right. From what? From the first state, which is P1, V1, pressure 1, V1, to the second state, P2, V2. P2 and V2. Pressure number 2 and the second volume, the final volume, V2. Given the gamma, especially gamma, which is equal to 5/3 in this case. A, the final volume V2. The final volume V2. How much is it? Adiabatic process. It means that the rule P1 V1 to the power of gamma equals to P2 multiplied by V2 to the power of gamma. Of course, all of them are equal to a constant. We don't pay attention for the constant, but we know that P1 V1 power gamma equals P2 V2 power gamma. This can be proved in your lessons. By the way, the volume V2 power gamma is equal to P1 over P2 multiplied by V1 power gamma. But we need V2. So here we make the root in the order of gamma. So V2, like this, it comes equals to the P1 over P2, and be careful here, coming to the power of 1 over gamma multiplied by V1. These are rules of exponents, so V1 without gamma. Numerical application, and we finish part A. V2 is equal to, now it's easy to know, pressure 1 and pressure 2. Pressure 1 was 1, pressure 2 was 3 in bar, bar and bar can be cancelled out, to the power of the inverse of gamma, which is 3 over 5. 3 over 5. All of this multiplied by the 10 liters. So you will find the volume in liters, because you have conserved liters here. This calculus gives 5.17 almost liters. This is for A. B. The work exchanged by the gas with the external environment. So we need to find the work. The work here is always a path function. So minus integration of P dV. And it comes exactly the pressure 2, you can prove this, and how to find finally P2 V2. I think it's not important to know why it comes P2 V2 minus P1 V1, be careful, without any exponent except 1. Sorry, P1 V1 here. So P1 V1. All of this over gamma minus 1. And this subject, if you need to find this expression, you have to integrate this form with P coming V to the power of gamma constant, because this is for the rule PV to the power of gamma is a constant. All of this because the process is an adiabatic. All right, this is one result. So you have this expression P2V2 minus P1V1 over gamma minus 1. You have everything. The P2, which is equal to 3 bars, so 3 multiply 10 to the power of 5. The pressure V, the volume V2, sorry, is equal to 5.17 liters. So you convert it to meter cubes. For the work must be in joule. So 10 to the power negative 3 minus P1 10 to the power of 5 pascals, here to the 5, multiplied by 10 liters, I mean 10 multiplied by 10 to the power of negative 3. And all of this divided by gamma, which is 5 over 3 minus 1. Be careful for this calculus, how to manipulate all these numbers in your calculator, and you will find finally 826.5 joules. It's a compression, so the work is done by the environment on the system. so it's positive. This is your work. C. We ask for the change in the internal energy of this gas. For the change, it means delta U. Delta U in formula is equal to work plus the heat Q. But another result, if it's adiabatic compression process, automatically the Q is equal to 0. This is very important to know about. So Q equals to 0. And this gives us the variation in the internal, the change in U, still work. The work is done in B, means 826.5 joules. So it's easy to deduce this. Still now, the variation in the temperature of the gas without calculating its initial temperature, because we don't know about T1, the first temperature. D. How to find the solution of this? Also, as delta U, I mean the internal energy in change, function state, equals to N, number of moles, multiplied by the constant C when we withdraw it with a constant volume, multiplied by delta T, the change in temperature. So we focus on delta T now. This undergoes delta T equals to what? Delta variation in the internal, the change in the internal energy over N multiplied by the constant CV. But we have no idea about N till now and no idea about CV. We have to find them. N number of moles is mass over molar mass of the species, which is the helium, molar mass of the helium. The mass used is 2 grams and the molar mass of the helium is 4. This is well known before in previous lessons of chemistry. 2 over 4, which is equal to 0.5 mole. Well done. Still now CV. How to find CV like this? There is a rule that Cp minus Cv, constant at pressure, measured at pressure when it is constant, minus Cv is always equals to R. This difference is always equals to R. If we think to divide by Cv, left side and the right side, this comes Cp minus Cv over Cv here equals R over Cv. And this Cp over Cv, which is equal to gamma, minus 1, which is equal to R over Cv. Forget this. To know finally that when you inverse, you will get Cv equals R over gamma minus 1. Now everything is there. So you return to your question. The variation in temperature equals delta U, which is, I think, which is the value of your work. So it's just a work. You substitute delta U by work over NCV, over NCV, NCV. But you have everything for CV. CV is R over gamma minus 1. So fraction under fraction, you get gamma minus 1, of course, times work, over NR. NR. Numerical application for this, delta T equals to, I think it's easy, gamma minus 1, which is 5 over 3 minus 1, times the work 826.5, and then divide by the number of moles 0.5, and the data for R, the given R 8.32 multiplied by 1 mole joule per mole per degree Kelvin, so 8.32 times the 1, nothing would change, and you find this calculus, you will get 132 degree, almost 132 degree Kelvin. If we recapitulate this, you see that in a Clapeyron diagram, I mean pressure versus volume, first you have a volume of 10 liters with a compression until 5, let's say here 5.17. From the pressure 1 bar until the pressure of 10 bars, here, let's say here, 10 bars, and your adiabatic process was like this until this state. So in the direction from 10 to 5.15. From temperature 1 until sure temperature 2. Just we know here that the variation from 1 to 2, which is temperature 2 minus temperature 1, equals 132 degree. It depends on temperature T1. Depends on temperature T1. Here, sure, when it is adiabatic, so sure, no heat, just a work W. Thank you for watching this solution.